I would like to talk about one phenomenon in the theory of functional differential equations, and demonstrate it in a situation where the highest derivative of the unknown function are present in an equation for the arguments t and t multiplied by q plus h simultaneously. In the literature, it is often referred to as equations with rescaling. So equations with rescaling. And there is indeed a very extensive bibliography on the pantograph equation and its various one-dimensional generalizations. The surge of interest to the pantograph equation falls on 1970s due to an engineering application, namely a mathematical model for the dynamic interaction between a contact wire and a locomotive current collector system. But earlier, in 1944, academician Albert Zuman obtained this equation in the problem of light absorption by nebulae. Later, in the 1980s, the pantograph equation emerged in the problems in biology, in the problems of cell growth and reproduction. So the pantograph-like equation, and there are some other applications as well. And so the pantograph-like equations are model ones in describing a number of phenomena. And historically, they appeared almost simultaneously with differential difference equations. We consider elliptic analogues of such equations. And we do it in the spirit of works by Alexander Leonidovich Skubachevsky, where the theory of boundary value problems for differential difference equations in bounded domains was constructed as a source for which at the very beginning were the problems in the elasticity theory, the problems of multi-layer shells and plates, and also elliptic problems with non-local boundary conditions. Of course, the equations that I'm talking about today they are slightly related, indirectly related to the pantograph equation and what it describes. The study of boundary value problems for functional differential equations with rescaling and the higher derivatives was initiated by American mathematician Kenneth Cook, co-author of Richard Bellman of the book Differential Difference Equations, and the study also began in the one-dimensional case. On the other hand, according to the methods involved and the results obtained, these equations are far from differential difference equations. And when it comes to elliptic functional differential equations, the equations with rescaling play here the same role as the pantograph-like equation in the general theory of functional differential equations, having some characteristic properties such as non-isometric transformations and the presence of fixed points attracting orbits and so on. I would also like to mention that a different, more abstract view of elliptic functional differential equations with contraction-like mappings can be found in the papers by Anatoly Borisovich Antonevich, Boris Yurievich Sternin, and Anton Yurievich Savin, where a number of interesting, important results in the theory of index were obtained. So let's get down with some applications of elliptic PDEs, and let's get down to the business. So I would like to start with the following lemma concerning the abstract Dirichlet problem. In this lemma, we deal with a family of continuous sesquilinear forms on the Sobolev space H1 with a zero trace on the boundary. This family depends on some parameter P, which will be concretized, specified later, a bit later. And this family of sesquilinear forms must satisfy the following two requirements given by inequalities 1 and 2. I'll say a few words about the meaning of these inequalities. Then there exists a unique solution U pi to the identity, which is the formulation of the abstract Dirichlet problem, and which is important. We have the convergence of under the above conditions. We have the convergence of this family of solutions to the solution of the limit problem. Here is the proof. I omit the existence result. It's absolutely standard, but the continuous dependence is also not difficult. Here we estimate the difference in the H1 norm by this two constants, magnitudes, which the first one from inequality 1 and the second is here. And in application to functional differential equations, this parameter P is responsible for transformations of the argument, and it is supposed for closed values of P that the corresponding transformations are also closed in some sense. So, and roughly speaking, relation 1 is an easy consequence of the mean square continuity of functions from L2. And the whole matter comes down to coerciveness, coercivity condition 2. And the principal moment is that it must hold uniformly with respect to the parameter P and in some neighborhood of P0. And we then call it the uniform coerciveness conditions, UC. And it's very important to know that the fulfillment of this inequality for the fixed value P0 does not mean uniform coercivity in a neighborhood of P0, no matter how small this neighborhood is. So, in the theory of differential equations and functional differential equations, inequality 2 is known as the Gordon type inequality, and the corresponding operator associated with the sesquilinear form is called strongly elliptic. And a few words about the coercivity problem, which is the problem of finding necessary and sufficient conditions for strong ellipticity in algebraic terms. So everyone knows the classical papers by Wyszynski and Gordon, where they show that the Gordon inequality is equivalent to the classical definition of strong ellipticity. For differential difference equations with commensurable shifts, the coercivity problem was solved in the papers by Skubachevsky. There he showed that the Gordon type inequality is reduced to positive definiteness of a finite set of some matrix polynomials. And this topic was also studied for functional differential equations with isotropic or orthotropic compressions. So first of all, we consider the following Dirichlet problem for a differential difference equation in a cylindrical domain. And here are our difference operators. They can contain only shifts along the x1 axis. And all the shifts are proportional to 1 epsilon. So parameter pi is epsilon in this example. And here are our ciscollinear form. And for a fixed value of epsilon, problem 3 is a very simple, very special case of problem studied by Skubachevsky. And and the majority of results depend on the behavior on some matrices or some matrix polynomials. But now we consider this problem for all arbitrarily small values of epsilon, and we let epsilon go to 0. And for epsilon 0, we have a differential equation. So here, how necessary and sufficient condition for the uniform coercivity look like in this case. Note that this is not the standard usual symbol of a differential difference equation. First of all, we have here variable eta independent of psi. And then you cannot find epsilon here. It looks like as we have a differential difference operator with integer shifts. But it can be explained in the following way. For a fixed interval in the x1 direction, when we let epsilon be very small, when epsilon go to 0, it has the same effect as if we fix our epsilon, our epsilon, but expand our domain, expand our cylinder. So in the limit, we have an infinite cylinder with a fixed shift, with a difference operator containing the fixed shifts, something like that. So if condition 4 is fulfilled, then problem 3 has a unique solution for all values of epsilon. And this family of solution converges in H1 norm to the solution of the limit Dirichlet problem for a strongly elliptic differential equation. But what is important here? That the condition of strong ellipticity of the limit differential equation is just this. And it is obviously weaker than 4. So here we require that the real part of A is positive for all real eta, and here only for eta equal to 1. So much weaker. And the second example, in the second example, we consider an arbitrary bounded domain in Rn containing the origin. This is very important. And we consider the operator of the very similar structure. But now, instead of difference operators, we consider operators with rescaling. And all the parameters, all the scaling parameters here are positive powers, negative or positive, of 1 parameter q, greater than 1. And for a fixed value of q, the necessary and sufficient condition for the Galenic type inequality has the following form. So the dependence of q is easily seen here. But now we consider all the values of q greater than 1 in the neighborhood of q equal to 1, and we let q go to 1. For q equal to 1, we formally have a differential equation, and it is the same differential equation as in the previous problem. So for when when we have fixed shifts and fixed scaling parameters, these problems are very different. But they have the same limit problem, limit differential equation, and the necessary and sufficient conditions for the uniform coercivity are the same. They are the same. So the difference disappears here. Here are two simple examples. So what we can see that uniform coercivity in this case for this equation is that the modulus of the real part of B is less than 1/2. And for this equation, the uniform coercivity is equal to the absolute value of B less than 1. So it can be written in the explicit way. Next, we make the situation a bit more interesting. We consider an equation with two independent scaling parameters, unlike in the previous case. And we fix one of them, Q, and let the parameter P range in some segment. And we want to establish the existence of a unique generalized solution of the Dirichlet problem as P runs through this segment, and to study the behavior of the family of solutions UP as P goes to 1. Now the formal limit equation is already an equation with rescaling. And here are the necessary and sufficient conditions for the uniform coercivity in this case. While a necessary and sufficient condition for the Gordon type inequality for the limit equation, where P is taken equal to 1, looks as follows. So they are different. This is much weaker. So if the coefficients are such that the following two-sided inequality is satisfied, then being strongly elliptic for P equal to 1, our equation loses this property for P greater than 1. For example, the equation like this. If A, B, and C satisfy this inequality, then this equation is strongly elliptic only for P equal to 1. And this example shows the following property. It shows what can happen in this situation. Fix any arbitrary small alpha, positive alpha, and consider this equation. Alpha is arbitrarily small. So this term is, we can say it's almost negligible in the term of its norm. So it's and for P equal to 1, the boundary value problem is uniquely solvable, and all the general solutions are smooth. While for P greater than 1, arbitrarily close to 1, the boundary value problem possesses an infinite dimensional null space and non-smooth generalized solution. And this is in the case where alpha is arbitrarily small. So just the presence of this term with arbitrarily small coefficient leads to this effect. So let us now consider the case where both of the parameters are fixed. And in doing this, we assume then P and Q are such that their logarithms are incommensurable. This is the principal assumption here. And we are interested when is there a positive gamma such that this inequality holds for all u smooth compactly supported functions. And for this fixed P and Q, two parameters fixed. And this theorem gives the answer. So this inequality gives us the necessary and sufficient conditions for, we can say, strong ellipticity in the case where P and Q are fixed parameters. And very important consequences of this theorem, that being strong elliptic for fixed P and Q, such that their logarithms are incommensurable. We can say P and Q are multiplicatively incommensurable in this case. So being strongly elliptic for fixed P and Q, the equation remains strongly elliptic for all closed values as well. So the opposite situation here. Strong ellipticity for fixed P and Q and also in the neighborhood here. Moreover, it is strongly elliptic for all values from these ranges. And under the condition, the equation is strongly elliptic for all P and Q close to 1. And in the above cases, the Gordon type inequality holds uniformly with respect to the parameters P and Q. But this is not the case if our scaling parameters are commensurable. And then the first remark is no longer true. For example, the criterion for the strong ellipticity of this equation, where Q is taken equal to P squared, is the inequality. This inequality can be explicitly written here, and differs from the inequality for the multiplicative incommensurable. So we cannot just put here P square instead of Q. We get the very distinct inequality in this case. So the condition for Q equal to P square is far away from the condition for Q in a neighborhood of P square, no matter how close they are. And to explain the difference between these two cases, just consider only functional operators with rescaling for the simplicity. For P greater than 1, introduce the unitary operator P. And the commutative B star algebra, A Gothic P, of bounded operators in the space L2, generated by the operator P, which is the closure with respect to the operator norm of all these finite sums. And the Gelfand theory said that this algebra is isometrically isomorphic to the algebra of continuous function in the compact space of maximal ideals of our algebra A. And the Gelfand transform of this operator acts as a homeomorphism of the maximal ideal space onto the spectrum of the operator P, where the spectrum is the entire unit circle. But now, given two numbers P and Q multiplicatively incommensurable, consider the two unitary operators, P and Q, yes, they're the same, but with multiplicatively incommensurable scaling parameters. And we consider the commutative B star algebra obtained by the closure of the finite sums. So the algebra with two generators. The representation of an operator in the form of the sum is unique. And the key point is that we can estimate the norm of this operator from below by its coefficients. This is the key point, which helps us to answer the question. So we know that there is again an isometric isomorphism between our algebra and the algebra of C on the space of maximal ideals. But what is actually this space? And we can prove that the space of maximal ideals is homeomorphic to the two-dimensional torus. So in other words, the space of maximal ideas in the case is just the direct product of the maximal ideal spaces for these algebras generated by one of these operators alone. So this correspondence is uniquely extended to an isometric isomorphism of the algebra onto the algebra of continuous functions on the torus. And the norm of an operator equals the maximum of the absolute value of its symbol on the torus. And example, the norm of this operator is equals to this. Well, this is the necessary and sufficient condition for the positive definiteness of its Hermitian part. At the same time, the norm of the operator, where Q is taken to P squared, is equal to the maximum of the square root of this expression. We calculate this, and this is less than this. So the norm and the spectrum of the operator, this operator, change abruptly in a neighborhood of the value of Q equal to P squared. So here we have stability. We have stability for multiplicatively incommensurable scaling parameters, and instability in a neighborhood of multiplicatively commensurable parameters. So I stop here. Thank you very much.